Welcome! In this session, we'll be diving into problem number 1979, find greatest common divisor of array. This is a classic problem that explores fundamental concepts in mathematics and programming. Stay tuned as we break it down step by step and explore an efficient solution. In this problem, we are tasked with finding the greatest common divisor, or GCD, of an array of integers. Specifically, we need to determine the GCD of the smallest number and the largest number in the array. The greatest common divisor is defined as the largest positive integer that evenly divides two given numbers without leaving a remainder. The input is an array of integers called nums, which will always have at least two elements and can have a maximum length of 1000. Each individual number in the array falls within the range of 1 to 10,000. Our goal is to return a single integer, which represents the GCD of the smallest and largest numbers from the array. Let's look at an example to understand this better. Suppose the input is an array nums containing the values 2, 5, 6, 9, 10. In this case, the smallest number in the array is 2, and the largest number is 10. To calculate the GCD of these two numbers, we determine the largest positive integer that divides both 2 and 10 evenly. That number is 2, which is our output. This shows how we extract the smallest and largest numbers and compute their GCD. Now, consider another example where the input array is 7, 5, 6, 8, 3. Here, the smallest number is 3, and the largest number is 8. The greatest common divisor of 3 and 8 is 1, since there are no positive integers other than 1 that divide both 3 and 8 evenly. Therefore, the output is 1. For another scenario, if the array is 3, 3, where all elements are the same, both the smallest and largest numbers are 3. In this case, the GCD of 3 and 3 is simply 3, which is what we return as the output. To summarize, the problem includes a few important constraints. The input array will always have at least two elements, and all elements are positive integers, ensuring that the GCD is always well defined. The array can contain duplicate values, and it's also possible for the smallest and largest numbers to be the same, as we saw in the example, 3, 3. These edge cases highlight that our solution must account for such scenarios. By focusing on the smallest and largest numbers in the array, we can efficiently compute their greatest common divisor and ensure our solution meets the problem's requirements. To solve the problem of finding the greatest common divisor, or GCD, of an integer array, we explored two main approaches. The first is the brute force approach. The key idea here is that the GCD of the entire array is determined solely by the smallest and largest numbers in the array. Based on this, we can iterate through all integers from 1 up to the smallest number in the array and check which of these integers divide both the smallest and largest numbers without a remainder. To implement this, we first identify the smallest and largest numbers in the array, then iterate through all potential divisors up to the smaller of these two numbers. As we find divisors that divide both numbers, we track the largest one, which will be our GCD. While this approach is simple and intuitive, its inefficiency becomes apparent when dealing with large numbers, as iterating through all possible divisors can be time-consuming. Specifically, the time complexity is O, n plus min, a, b, where n is the size of the array and a and b are the smallest and largest numbers in the array. This limitation led us to consider a more efficient alternative, the Euclidean algorithm. The Euclidean algorithm provides a much more optimized way of finding the GCD of two numbers. This algorithm works by repeatedly replacing the larger number with the remainder obtained when dividing the two numbers, continuing this process until one of the numbers becomes 0. At that point, the other number is the GCD. To apply this to our problem, we first find the smallest and largest numbers in the array, and then use the Euclidean algorithm to compute their GCD directly. This eliminates the need to iterate through all potential divisors. The time complexity of this approach is much better, as finding the smallest and largest numbers takes O, n, and applying the Euclidean algorithm runs in O, log, min, a, b. Together, this gives an overall complexity of O, n plus log, min, a, b. This approach is not only faster but also more scalable, making it ideal for arrays with large numbers. For these reasons, we chose the Euclidean algorithm as our strategy. It is efficient, simple to implement once the smallest and largest numbers are identified, and it scales well even for arrays with a wide range of values. A key observation that simplifies this problem is that the GCD of the array depends only on its smallest and largest elements. This insight eliminates the need to compute the GCD of all possible pairs of numbers in the array, significantly reducing computational complexity. By leveraging the Euclidean algorithm, we further ensure that the solution is efficient, as it avoids the inefficiencies of iterating through all possible divisors. However, there are trade-offs to consider. While the brute force approach is easier to understand conceptually, it becomes impractical for large numbers due to its higher time complexity. On the other hand, the Euclidean algorithm, while optimal in terms of both time and space complexity, requires a clear understanding of the underlying mathematical principle. Ultimately, the chosen approach delivers the best balance between efficiency and simplicity. The final analysis confirms this. The time complexity of the solution is O, n plus log, min, a, b, where n is the size of the array, and a and b are the smallest and largest numbers. The space complexity is O, 1, as the algorithm operates using only a constant amount of extra space. To solve the problem of finding the greatest common divisor, or GCD, of an array of integers, we can simplify the task significantly by leveraging a key mathematical insight. The GCD of an array is determined entirely by the GCD of its smallest and largest elements. This is because the GCD operation is associative and commutative, meaning we don't need to compute the GCD for all pairs of numbers in the array. Instead, we reduce the problem to just two numbers, the smallest and largest values in the array. This reduction ensures that the solution is both efficient and straightforward to implement. Now, let's break the solution into a clear, step-by-step plan. First, we locate the smallest and largest values in the array, which we'll refer to as min_val and max_val. This can be done efficiently in a single traversal of the array. The reasoning here is simple. These two values are the key contributors to the GCD computation. Once we have min_val and max_val, we apply the Euclidean algorithm to calculate their GCD. The Euclidean algorithm is a classic method for GCD calculation. We repeatedly replace the larger number with the remainder of its division by the smaller number, until the remainder becomes 0. At that point, the smaller number is the GCD. This method is efficient because it reduces the size of the numbers involved in each step, and it works due to the mathematical properties of divisors. Additionally, the Euclidean algorithm operates in logarithmic time with respect to the smaller of the two numbers, making it highly efficient. There are a few important insights to highlight about this approach. First, by reducing the problem to just two numbers, the smallest and largest elements in the array, we greatly simplify the computation. This reduction is based on the property that the GCD of the array is equivalent to the GCD of these two extremes. Second, the Euclidean algorithm is optimal for GCD calculations due to its logarithmic complexity, ensuring that the computation is fast even for large numbers. Finally, finding the smallest and largest values in the array requires only a single traversal, which runs in linear time. Together, these steps create an algorithm that is both time-efficient and space-efficient. From a data structure perspective, we simply use the input array to find min_val and max_val, and we store these values in variables. This minimal use of resources ensures the space complexity remains constant. Let's take a closer look at the key operations involved in this algorithm. First, finding min_val and max_val is accomplished in a single traversal of the array, which runs in O, n, time. Next, we compute the GCD using the Euclidean algorithm, which operates in O, log, min_val, time. Combining these two steps gives us a complete algorithm. The process begins by initializing min_val and max_val to extreme values, such as infinity and -infinity. As we traverse the array, we update these variables whenever we encounter smaller or larger values. Once the traversal is complete, we apply the Euclidean algorithm. This involves iteratively computing the remainder of min_val divided by max_val, updating the variables accordingly, until the remainder becomes 0. At that point, min_val holds the GCD, which we return as the result. This step-by-step approach ensures clarity and efficiency. The time complexity of this algorithm is straightforward to analyze. Finding the smallest and largest elements in the array requires O, n, time, as we traverse the array once. Computing the GCD using the Euclidean algorithm takes O, log, min_val, time, as the number of iterations depends on the smaller of the two numbers. Combining these, the total time complexity is O, n plus log, min_val. For space complexity, the algorithm is highly efficient, using only a few variables, min_val, max_val, and remainder. This means the space complexity is O, 1, or constant. Additionally, the algorithm handles edge cases seamlessly. If the array contains only two elements, the algorithm directly computes their GCD. Duplicates in the array do not affect the result, as they do not change the smallest or largest values. Negative numbers are also handled naturally, as the modulus operator ensures that the GCD remains positive. Let's walk through an example to see the algorithm in action. Consider the input array nums equals 12, 15, 18, 21, 24. First, we find the smallest and largest values in the array. Here, min_val is 12 and max_val is 24. Next, we apply the Euclidean algorithm. We compute the remainder of 24 divided by 12, which is 0. At this point, we update min_val to 12 and max_val to 0. Since max_val is now 0, the GCD is the current value of min_val, which is 12. Thus, the output of the algorithm is 12. This example demonstrates how the algorithm efficiently reduces the problem and computes the GCD step by step. Now let's consider another example with negative numbers. Take the input array nums equals -8, -4, -2. Here, the smallest value is min_val equals -8, and the largest value is max_val equals -2. Applying the Euclidean algorithm, we compute the remainder of -8 divided by -2, which is 0. We then update min_val to -2 and max_val to 0. Since max_val is 0, the GCD is the absolute value of min_val, which is 2. The algorithm correctly handles negative numbers, returning a positive GCD as expected. The output in this case is 2. This Python implementation solves LeetCode problem 1979, find greatest common divisor of array. The function findGCD takes an input list nums and calculates the greatest common divisor, GCD, of the smallest and largest numbers in the array. 1. Importing GCD, we import the GCD function from Python's built-in math module. The GCD function efficiently calculates the greatest common divisor of two integers using the Euclidean algorithm. 2. Finding the smallest and largest numbers, the min and max functions are used to find the smallest and largest elements in the array nums. Since the GCD of an array can be determined solely from these two values, due to the commutative and associative properties of the GCD operation, this step simplifies the problem significantly. 3. Calculating the GCD, using the GCD function, we compute the GCD of the smallest and largest numbers. The result is then returned as the output. ###example. Suppose the input array is nums equals 2, 5, 6, 9, 10. The smallest number is 2, and the largest is 10. The GCD of 2 and 10 is 2, which is returned as the result. ###complexity analysis. Time complexity, O, n, for finding the smallest and largest numbers in the array, where n is the length of nums. The GCD operation takes O, log, min, a, b, where a and b are the two numbers involved. Space complexity, O, 1, as no additional space is required beyond a few variables. This solution is efficient and adheres to the constraints of the problem. Here, we start by importing the necessary package java.util** and defining our class solution with the method findGCD. This method takes an integer array nums as input. The first step inside the method is to identify the smallest and largest numbers in the array. To do this, we initialize two variables, smallest and largest, with integer.max_value and integer.min_value respectively. Then, we iterate through the array using an enhanced for loop. During each iteration, we check if the current number is smaller than smallest or larger than largest, and update these variables accordingly. Once we have the smallest and largest numbers, we move on to compute their greatest common divisor, or GCD, using a helper method called GCD. This helper method implements the Euclidean algorithm, and we pass smallest and largest as arguments to it. The GCD helper method is implemented using a while loop. The loop continues as long as the second number, b, is not 0. Inside the loop, we use the Euclidean algorithm to compute the GCD. First, we store the value of b in a temporary variable temp. Then, we update b to the remainder of the division between a and b, and finally assign the value of temp to a. This process continues until b becomes 0, at which point the value of a is returned as the GCD. This efficient algorithm ensures that we find the greatest common divisor of the two numbers with minimal computation. To solve the problem of finding the greatest common divisor of an array, we start with the first example where the input array is 2, 5, 6, 9, 10. The first step is to identify the smallest and largest numbers in this array. Using Python's built-in min and max functions, we find that the smallest number is 2 and the largest number is 10. Once we have these two numbers, the next step is to compute their greatest common divisor, or GCD. Using Python's math.gcd function, we calculate the GCD of 2 and 10. The GCD is 2 because it is the largest number that divides both 2 and 10 evenly, without leaving a remainder. Thus, the output of the function for this example is 2. Now, let's apply the same process to another example where the input array is 3, 15, 21, 30. Again, the first step is to identify the smallest and largest numbers in the array. The smallest number here is 3, and the largest number is 30. With these two numbers identified, we proceed to calculate their greatest common divisor using the math.gcd function. We find the GCD of 3 and 30 to be 3, because 3 is the largest number that divides both 3 and 30 without leaving a remainder. Therefore, the function returns the value 3 as the result for this example. In the final example, the input array is 8, 12, 16, 24. Again, the smallest and largest numbers are determined first. Here, the smallest number is 8, and the largest number is 24. Using the math.gcd function, we calculate the greatest common divisor of these two numbers. The GCD of 8 and 24 is 8, since 8 is the largest number that divides both 8 and 24 evenly. As a result, the function outputs the value 8 for this example. This concludes the process, where we consistently identify the smallest and largest numbers and compute their GCD using Python's built-in tools. To analyze the time complexity of this algorithm, we can break it down into three main steps. First, we use the min function to find the smallest number in the array. This involves iterating through the array once, which gives us a time complexity of O(n), where n is the length of the array. Next, we use the max function to locate the largest number in the array. Similar to the min function, this also involves a single pass through the array, resulting in another O(n) for this step. Finally, we compute the greatest common divisor, or GCD, between the smallest and largest numbers using the GCD function from Python's math module. The GCD function employs the Euclidean algorithm, which has a time complexity of O log min a, b, where a and b are the input numbers. In our case, a is the smallest number, and b is the largest number. These steps together form the foundation of the algorithm's time complexity. When we combine these steps, the overall time complexity becomes the sum of the individual components, O(n), for finding the minimum number, O(n), for finding the maximum number, and O log min, smallest, largest, for the GCD computation. Among these, the O(n) terms from the min and max functions dominate, since they scale linearly with the size of the array. As a result, the overall time complexity of the algorithm simplifies to O(n). Now, let's consider the space complexity. First, the input array itself does not contribute additional memory usage, as it is provided as input. Second, the temporary variables smallest and largest are used to store the results of the min and max computations, and these require only O(1) additional space. This means that the algorithm uses very little extra memory so far. Additionally, the GCD function is highly space efficient. It operates using the Euclidean algorithm, which does not require any extra memory beyond the input values themselves. Since the space required by the algorithm is limited to the temporary variables in the input array, the overall space complexity is O(1), indicating constant space usage regardless of the size of the input. For comparison, consider a brute force approach to solving this problem. In a brute force method, we would iterate over all possible pairs of numbers in the array to compute their GCDs, and then combine these GCD results to find the overall GCD. This would require looping through all pairs, which has a time complexity of O(n squared) for the iterations, and computing the GCD for each pair, which adds an additional O log, min, nums, I, nums, j factor. This results in an overall time complexity of O(n squared asterisk log, min, nums, I, nums, j, which is far less efficient than the current solution. The current algorithm optimizes this process significantly by focusing only on the smallest and largest numbers in the array. This reduction eliminates the need to consider all pairs, drastically improving the efficiency. Furthermore, the use of the Euclidean algorithm ensures that the GCD computation is performed as efficiently as possible. Together, these optimizations result in a time complexity of O(n), which is much more suitable for large input sizes. The space complexity also remains optimal at O(1), since no additional memory is used beyond a few temporary variables. Analyzing the best, average, and worst-case scenarios, we can see that the time complexity remains O(n) in all cases. In the best case, when the array has only two elements, the number of iterations for min and max is reduced, resulting in a lower constant factor. In the average case, with n elements of random values, every element still needs to be checked for min and max. In the worst case, when the array has a large range between the smallest and largest numbers, the GCD computation may take slightly longer, but this does not affect the dominant O(n) term. To mathematically justify the big O analysis, note that the min and max functions each iterate through the array once, contributing O(n) for each operation. The GCD computation adds O log, min, smallest, largest, to the time complexity. When combining these terms, the O(n) contributions from min and max dominate, making the overall time complexity O(n). The space complexity, on the other hand, remains O(1), as the algorithm only uses a constant amount of extra memory for temporary variables in the GCD computation. In conclusion, this algorithm is both time-efficient and space-efficient, making it a highly effective solution for finding the greatest common divisor of an array, especially when compared to brute force methods. When tackling this problem, there are some common mistakes to watch out for. First, overlooking edge cases can lead to errors. For instance, if the array is very small, such as having only two elements, or if all elements in the array are the same, the solution needs to handle these situations correctly. Take an array like 2, 2, the greatest common divisor is still 2, but failing to account for this could result in incorrect outputs. Another mistake is relying on inefficient brute force methods, like iterating through all numbers from 1 to the smallest number in the array to check for divisors. While this might work for small inputs, it becomes far too slow for larger arrays, especially when values reach up to 10,000. This approach has a time complexity of O(n asterisk min, nums, which is not optimal. Lastly, some assume that sorting the array is necessary to solve the problem. However, sorting has a time complexity of O(n log n, and it's completely avoidable since the minimum and maximum values can be found in linear time, O(n). Identifying and avoiding these pitfalls can significantly improve the efficiency and correctness of your solution. Another set of mistakes involves misunderstanding key concepts. Misusing built-in GCD functions is a frequent issue. In Python, for example, math.gcd operates on two numbers, so applying it directly to an array without reducing the elements won't give the expected result. You need to reduce the array step by step using the GCD function to avoid incorrect outputs. Additionally, some miss the opportunity to leverage modular arithmetic. A fundamental property of the GCD is that GCD A, B equals GCD B, %B. This property forms the basis of the Euclidean algorithm, which is the most efficient way to compute the GCD of two numbers. Ignoring this property often leads to unnecessarily complex or inefficient solutions. By understanding and correctly applying these concepts, you can ensure both clarity and efficiency in your approach. In interviews, it's important to focus on the most efficient strategies. A key insight for this problem is that the GCD of the entire array is always a divisor of the GCD of the minimum and maximum elements in the array. This means you don't need to check every element individually. Instead, you can focus on min, nums, and max, nums. Using the Euclidean algorithm to find the GCD of two numbers ensures optimal performance, with a time complexity of O log min a b. It's also essential to communicate clearly with your interviewer. For example, confirm whether the array only contains positive integers, as this can simplify your edge case handling. Recognizing patterns is another critical skill. Problems involving arrays and modular arithmetic often rely on the same principles, so identifying the GCD as a key operation can help you solve related problems efficiently. To practice, you can explore related LeetCode problems such as problem 1250, which checks 4 good arrays, or problem 1071, which involves the GCD of strings. These problems reinforce the fundamental concepts behind GCD calculations. There are alternative approaches to solving this problem, each with its own trade-offs. One efficient method is iterative reduction using the GCD function. By employing Python's reduce or a loop, you can iteratively calculate the GCD for the entire array. While this approach is efficient, it does require a solid understanding of how reduction mechanisms work. Another less common approach is prime factorization, which involves breaking down each number in the array into its prime factors and finding the common factors among them. However, this method is computationally expensive, with a time complexity of O and *sqrt, max, nums, and is generally impractical for large inputs. Finally, there's the brute force method of checking all divisors of the smallest number in the array to find the highest one shared by all elements. This is simple to implement and works well for small inputs, but its time complexity of O and *min, nums, makes it unsuitable for larger arrays. Choosing the right approach depends on the constraints of the problem and the size of the input. Great job! We've just tackled the problem of finding the greatest common divisor of an array using an efficient and elegant approach. Remember, mastering these core concepts can significantly improve your problem-solving skills. Don't forget to practice more and share this video with fellow coders. See you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!